Okay, we are live now. Thank you.
Okay, thank you. Okay, so our speaker today is Nina-Elisabeth Nèmec. She did a PhD at the Max Planck Institute in Göttingen. Then she also did a postdoc at the University of Göttingen, and now she's a Marie Curie Fellow here at the Institute. She joined the group of Ignacio Ribas. And if you want to know what does she research, you will just have to listen to her talk. So thank you.
Thank you. Yeah, I'm technically somewhat a solar physicist by training, and I think that is quite unique in this institute, I might say. Ignacio and I went to a solar physics conference last week, and maybe I should start calling myself a solar astrophysicist. I think that would make more sense. And yeah, I now hunt for exoplanets, so I will tell you the story of how I ended up here, essentially. Come on. If you search for exoplanet in the ADS abstract server, you see that the field has quite a lot of attention still. So if you look here, this is a little bump here. We learn a little bit from Kepler. The first exoplanet around a solar-like star was discovered in 1992. And now we're essentially in an era with JWST where we not only find exoplanets, but where we can characterize the atmospheres. And I think that's quite an incredible development. So when we look for exoplanets, there's different techniques. Spectroscopy is one of them. We essentially look for signatures in the spectrum that is shifting depending whether the planet is moving away from us or towards us. And essentially, you measure the wobble of the host star that is introduced by the gravitational pull by the planet. The cheapest way to look for an exoplanet is still transit photometry. So your star is a light source, and if your planet crosses in front of it, you see this very nice dip. And then one step further is essentially transmission spectroscopy, where we think that a planet might have an atmosphere. And then depending on the atmospheric composition, if you look at different wavelengths, you should get different depths in your transit. And when it comes to finding Earth's twin, technical developments have also been incredible. So for spectroscopy, we actually need around 10 centimeters per second of stability in instruments, which we currently have. And if we look at the transmission spectroscopy with JWST, on some targets, we also have the precision of 10 ppm that would also be needed to detect an Earth-like planet. What I'm showing you here is the planet mass, or the mass times the sinus I, as a function of the orbital period, and here the planet radius in Earth radius as a function of the orbital period as well. And what you see here, these dots, these clouds here, are the solar system planets. So what we're seeing are completely different planets than we know in our solar system. And you can also see that, so this would be Earth and Venus here. And here, there's not many planets around them. Matter of fact, barely any. And well, that leads to the question, like, why haven't we found Earth's twin yet, despite all this fantastic stability and precision of our instruments? One thing, especially in that plot, that has to be noted, Earth orbits the sun in a year, right? So if you want to detect a planet like Earth, you have to observe your system for several years. So that's one of the biases. However, we still don't get anything close to an Earth-mass planet either. Well, it gets worse when we look at now transmission spectroscopy. So this is the TRAPPIST-1 system. It's, I think, the exoplanets community's favorite system. It's a ultra cool, very cool M-dwarf. So nothing like our sun. And the system has, I think, 6 or 7 known planets. Some of them are actually close to being Earth-sized. And this observation, so those are the observations. Here the data is in this crosses. And those observations are taken 2 days apart. So you see clearly you detect something, you don't detect the same signal. So within those 2 days, something happens. So what can happen? Either we have somewhat a rapidly changing planetary atmosphere, because you also see here that if you do retrievals and fitting, you also get two completely different solutions for the planetary atmosphere. Or is there some variability coming from the background? And in this case, the background is the star. And stars are not constant entities. So this is our own star, this is the sun. First of all, you already see that this is not one color. There's a color gradient, which is called center to limb variations. We're looking at something that's a little bit brighter in the disk and something that's dimmer towards the limb. And this surface is not even immaculate either. So you see that it's like something that's like spots going on. And this leads me now to the formulation of the stellar activity conundrum. If we just look at the sun, we know what the sun is doing at the surface at most of the time, because we have missions that observe the sun essentially 24/7. We know how the solar activity influences all observables. And when we now go to stars, we just have our observables. We don't know what the star is doing on its surface, how the surface is looking. The inverse problem can be solved. I will talk about this if I have time towards the end of my talk. However, the approach that I took during my PhD is we know how the sun works to some degree. We know how the solar activity influences our observables. So can we actually now take the solar paradigm and extend it to stars that are like the sun, and maybe a bit different than the sun, and just see if we can explain some of those observables. So my talk is essentially structured in 4 sections. I will first talk about the sun and what causes solar variability. I want to discuss how the sun is a sun-like star, how we now model solar and stellar spectra, and how we want to, well, maybe not solve this problem, but tackle this problem of the stellar activity contamination. What causes solar variability? Well, if we look at timescales of 5 minutes, this is essentially a Fourier transform of the solar spectrum. You see this peak here at 5 minutes. Those are the so-called P mode oscillations of the sun. And you also see a little bit of a bump of a signal here that's caused by granulation that you see here in this movie. So granulation is caused by the convection zone that is just underneath the surface. And what happens is that bubbles of hot material are being transported upwards. And once they cool down, material sort of flows back into the interior of the surface in these intergranular lanes. Those are real solar observations taken from, not even from space, those are ground-based observations. And the structures that we're seeing are around 1,000 kilometers in diameter. So what I think I also like about being solar physicists is that we have these observations of like in such great detail that we don't have for any other astronomical object. What I will be discussing mostly in the talk is variability on timescales larger than a day that is caused by magnetism on the sun. So most prominently here, you see, for instance, this 11-year cycle. But we also saw different variations. So what you're seeing here is this active region that crosses across the solar disk. And you also see that it's changing. So this is roughly half a solar rotation. It's very dynamic. I'm not sure if you can see it well, but there's this, it looks like a little bit of flicker going on. That is also real signal. That's the granulation signal that you can see. And just pause here. So we call this very unsurprisingly a sunspot. You see it's very fractured entity. And you also see that to some degree, sunspots are typically on the side on the size of the Earth projected on the sun. Shown here is the so-called total solar radiance. This is in stellar astrophysics, you would call this volumetric luminosity, essentially. And you see that this is not constant. In former times, actually, this has only been discovered in the last 150 years. It was actually believed that the sun is constant in its brightness. So you sometimes in old literature, you can see this TSI being called the solar constant. So you see here this very nice 11-year variation, and you also see day-to-day variation. So dips like this here are caused by the transit of these dark spot regions, but you also see that there's some net brightening going on, and this is caused by these regions here. We call them faculae for now. So you have something bright on the sun, the faculae, and you have something dark, the spots. And all of this drives this nice variability pattern. That's how we understand solar variability works. Now, we have a lot of data that's actually thanks to planet hunting missions. So with the Kepler telescope, we have 4 years of observations for over 100,000 stars. And the primary objective of Kepler was to find exoplanets, and all of the stellar variability studying, let that be magnetic activity, convective variability, or astroseismology, is to suddenly be a little bit of a byproduct. So we need to keep in mind that with the sun, we only have one star. We have space-based observations of solar brightness variations for 30, 40 years. We can do reconstructions further back in time up to 150,000 years back. And then we have this data for stars for 4 years, 100,000 stars. And we also have some ground-based data where we also have 50 years of data for roughly 150 stars. So we even see that some of these stars also exhibit cycles. In my talk, however, I will focus on comparing the sun to Kepler stars, mostly for time reasons, but we've also published work about this. As I said, Kepler was the most successful planet hunter. We're talking about 4,000 or 5,000 confirmed exoplanets that Kepler has found. And even though the mission actually has now been over for, I think, over 10 years, data is still analyzed and there's still new discoveries to be made. So shown here is now the variability as a function of the rotation period. And you see this, so this is for stars that have similar effective temperatures as the sun. So you see there's a little bit of a trend that if we go towards faster rotators, the variability increases slightly, but obviously there's a lot of scatter. But if you look at this bulk here, that seems to be the case. And if we now plot the sun here, it's somewhat down on this distribution. And we were wondering what happens there, because you could look at this plot and say, well, I mean, you claim those are sun-like stars. Well, the sun is not a sun-like star. And those claims have been made. So we wanted to look a bit further into what's causing all of that. So firstly, we identified 2 biases. We always look at the sun from the ecliptic plane, more or less. So we have the sun and the Earth, we look like this. Whereas if we have different systems, we don't know how we look at the star. So this is called the inclination angle, which is the angle between the line of sight of the observer and the stellar rotation axis. For the sun, this is roughly 90 degrees. For other stars, we have no idea. And secondly, for the sun, we can either measure the complete solar spectrum, or if you integrate it, you get the total solar radiance, whereas stars like Kepler, we observe them in some predefined passband in some more or less narrow wavelength regime. And we've published quite a bit on that. So the inclination, the difference in the inclination, different in the passbands of the 2 biases I want to address first. How we do this? We take the approach of the spectral and total solar irradiance reconstruction model. And this is now even the standard in what's done in modeling stellar variability. So you take some distribution of magnetic features. For the sun, we can take it from observations, or you take some sort of model. In our case, we use a surface flux transport model that gives you an idea of how other stars might look like on the surface. And then you convolve it with some spectrum from some library, and you get your observed variability. Those publications are all from the former ERC starting ground SOLVE, where I did my PhD in. So this is not an exhaustive list of what has been done in the past when it comes to that, but just within that group. And this model, SATIRE, has been really, really successful. So shown here is a so-called wavelet transform of the solar spectrum. In orange are the observations, and in black is the model. And you see that it overall fits quite nicely. So for the magnetic activity, we use the SATIRE approach. However, on timescales below a day, on a couple of hours, you also need to take into account granulation. We do that with the Murram code that I will be discussing towards the end of my talk. And what's already nice here is that, so this here is the 11-year solar cycle peak. And there is something here. That's the solar rotation period at around 27 days. The only thing that our model is not really capturing is this dip here. Those would be the solar P-mode oscillations that we didn't have present in our model. Well, so what we did is we decided that we use sun as a star observations. We took the observed solar spectrum and we convolved it with whatever passband is commonly used in stellar observations. And this is plotted here. So again, the TSI is how we observe the sun. And then shown here in the different filter passbands. So what we did, which is commonly done, is we took our light curve. So we used 22 years of data. We took 30-day chunks and we looked at the peak-to-peak variability that we then call these 30 metric. And you see that there's differences from passband to passband, which is not surprising. So Corot and the Gaia green passband are roughly centered where the sun has the maximum in its spectrum, but also the sun is not that variable there. And the reason why it's not that variable there is because our bright features, the faculae, and the dark features, the spots, they're sort of in a balance. If we go towards the red, we see, well, we would overestimate the solar variability a little bit if we take the TSI. However, it gets a little bit worse if we go towards the blue. So the solar variability in Gaia blue would actually be underestimated by roughly 30%, which is quite a lot. And that is because the sun is actually a little bit more variable towards the UV. The next thing, we can also look at the inclination. So this is how we would observe the sun. And you see again this nice dips and patterns that come from the transit of those active regions. If we now go towards a pole-bound observer, the variability signal is decreasing drastically. And also we observe a little bit of a different trigger for this variability. Because what happens here, we don't see features disappearing on the far side, but we see a feature that's emerging and then it's decaying. So we can sort of measure that decay of the features very nicely here, whereas the signal here is completely dominated by the stellar rotation. Yeah, this is just some more plots that show that depending on what passband you're using, you on average actually underestimating or overestimating the solar variability by 20%. And funnily enough, you still find literature today that still uses the TSI as the one measure of solar variability. Well, we can take all of this now into account, and we see that the sun is still low in its variability. There were a couple of papers, a little bit clickbait, if you ask me, my humble opinion, that claimed the sun is less active than solar-like stars. To the point where people said the sun is not a sun-like star, we need to call the sun something else. It was a bit of a weird time. Well, one of the problems is that it seems the sun-like stars are just missing in this picture. So we know from galactic evolution models, there should be more sun-like rotators. And there also should be more stars that have lower variability levels compared to the sun. So what these authors did, Timo Reiner and Anne in their study, they looked at what McQuillan et al. Called the periodic sample. This is essentially the sample for which McQuillan could detect rotation periods. And used the sun, so they added noise like it would be observed in the Kepler telescope. And what they found is that it seemed like there's two distinct distributions. So you would have the sun here, and then other stars more towards higher variability. However, what they then did is for stars with known effective temperatures close to the sun, they ignored whether they can capture the rotation period or not, and just calculated the variability. So now what you're seeing is that something is going wrong with the detection of rotation period, because all of a sudden, we take the black curve, the sun fits right in. So let me just also address this bias in detecting rotation periods. McQuillan et al. Used autocorrelation functions, and autocorrelation functions work really, really well if you have a signal that's somewhat self-similar. So it works well for a star like this, where you have a lot of signal and you also would see some periodicity. The sun looks like this. It looks like it's just noise. It's low in variability. The variability is low in amplitude. And also the sun is relatively irregular. So regions on a star like this might live relatively long, whereas we know that a spot on a sun lives maybe 100 days. So that's 3 rotation periods if you're lucky. So it's very hard for those techniques to pick up the rotation period. Well, but still, what's going on with those stars now? That was our next question. And there was a study with a toy model by ICE-CSIC et al. And they found that those stars can be explained by introducing what we call nesting. Now, nesting is not that much of a new concept in solar physics, because as we saw, the spot groups are not like one singular spots, some more or less spots that are grouping together. So on the sun, we most of the time see this like weak nesting, and then we introduce 2 different modes of nesting. So one is what we call free nesting. So the nests occur at some latitude and some longitude. And then we also have a separate mode of nesting, which is called active longitudes. So your regions can emerge at any latitude, but they're somewhat with some scatter fixed at a latitude. And this study here very nicely showed that if we increase this nesting, we can actually capture those stars fairly well. So we decided that we now want to take this step one further and actually go to more active stars. So this is the sun, essentially our solar-like rotator. And this is a star that is rotating 8 times faster than the sun. So what you see is that most of the field is actually centered at the poles. And this is consistent with observations that are around somewhere between 2 and 4 times of the rotation rate of the sun, you start forming those polar spots. And indeed, what we found that, so I'm just showing the most extreme cases that we considered in our study. If we just increase our activity with the rotation period, so let's say a star that's rotating 4 times as fast as the sun has 4 times more active regions, we barely capture this lower part of the distribution. And then depending on how far we take our clustering, nesting, clumping of active regions, we actually get towards the higher end and also towards this end. So what we concluded from that is that this dependence that is seen here for sun-like stars can be explained by increasing sort of the clumping of active regions. To finish this tail and biasing detection rotational periods, Santos et al. Took a step further. They used the autocorrelation function that McQuillan did, plus a wavelet analysis and machine learning. And indeed, they were actually able to find roughly 20,000 more target section of rotation periods compared to McQuillan. It still didn't fully match what we would have thought we would see from the galactic evolution models. So Reinhold et al. Took a different approach that's based on the gradient of the power spectrum, more specifically on the inflection point of the power spectrum. So this is solar rotation period, and we're looking at this part here, so between 10 and 3 days. And we know from the sun at this point, so this one is variable, but funnily enough, the inflection point is relatively stable for the sun. So they applied their method to the Kepler targets again, and compared to Santos, found again 10,000 more stars with detected rotation period. So now we're almost there where the galactic evolution model wants us to be. And I think what that also highlights, given that the ACF, wavelet analysis, and machine learning are not necessarily physics-based, I think this very nicely highlights the need again for having a physical understanding of what's causing brightness variations and what's causing all those biases. So I mentioned that we also need to rely on spectra for analysis. So this is relatively new work still, that's ongoing. I don't want to bother you too much, but I need to address radiative transfer fairly quickly. Most of us deal with radiative transfer in some way. So if you do extragalactic, you deal with extragalactic extinction. And to some degree, that also happens on the sun. So you have your light source somewhere, and then it passes through an atmosphere. And you need to understand what this atmosphere is doing to your ray of light. So this is one form of the radiative transfer equation. And what you want to solve is this called source term. And in reality, what you do is you look at tables, and you, through an iterative process, try to solve this equation that at the end gives you your atmosphere, and then you can do you can run some codes on it, and it gives you a spectrum. Most of these methods are still based on 1D, and I was mentioning convection, which is a 3D process. So there is something that we call mixing length theory that is applied to this spectra, that convection is somewhat taken account. And this is, again, just some list that's now currently used. Well, I already mentioned it. We're not dealing with 1D structures on the sun. We're dealing with 3D structures that are also governed by magnetic fields. So this convection here essentially looks like a little bit like mountains and valleys. So you're not looking at the same height in your atmosphere. So if you want to do this correctly, you would have to do your radiative transfer on every single point here to get the correct corresponding spectra for the atmospheric layer you're looking at. And it gets worse. When we now look at spots, they're governed by magnetic fields. So the spot in the center is dark. This is called the umbra. Then you have this not so dark layer called the penumbra. And then you see this is the convective pattern. Now, why is the umbra dark? Well, spots are manifestations of magnetic fields. And those magnetic fields are so strong that in the umbra can completely suppress convection. So all of a sudden, we're actually looking at a height in the atmosphere that is a little bit more like we're really looking at a depression that's called the Wilson depression or the Wilson effect. And that's also, I think, nicely seen here in the velocity field. So this is your velocity field that comes from the convection. In the penumbra, you see this like filament structure of velocities. This is called the Evershed flow. So it's essentially flows that somewhat go back into the solar interior. And again, the complete suppression of convection towards the center, towards the penumbra. Does it get more complicated? Yes, because we're also dealing with faculae. Faculae are somewhat like spots. They're just like smaller in size and have less strong fields. So what happens here is that they can still suppress convection, but not to this degree. So what's now causing the faculae to appear bright is that essentially convection and the heat that's coming from the convection is heating these walls here. So what you see here in this image is essentially not coming from the center of this flux tube, but from the walls of this flux tubes. And I will come back to this point actually towards the end of this talk again. Well, how could we now deal with that? Well, we need actually comprehensive 3D MHD simulations. Shown here is just one example. That's the Murram cube, the Murram code, sorry. And shown here is an example of, well, convection at different wavelengths. And Murram is not the only code that is available, but it is the only code that also takes into account magnetic fields. So in Murram, you can actually set it up to get spots as well. And I took the fun out of this little game here, but the left side here shows you the simulation from Murram, and the right side is the observation of an actual sunspot. And if you look closer, you see some differences. Some differences are mostly because of different path spans used, but more or less, this is strikingly similar. So that also motivated us to use Murram and go to different stars because we can't resolve surfaces of other stars. This is one of the most frustrating things for me coming from solar physics. We just don't know how stars look like. But with these simulations, we somewhat get a little bit of an idea. So G25, this is our sun essentially. K2, a little bit cooler, and then an M0 star, again, cooler, smaller. And you see that more or less the structure of having our dark center, so the umbra and the penumbra seems to persist, even though for an M dwarf, the penumbra is even more of a filament structure than it is on the sun. And also the velocity fields are getting are very similar. You see that the convection signal here on this M dwarf is actually a bit less strong, which has something to do that we're looking at a star that's very, very small. So we have we don't have high surface gravities, so convection is actually a little bit different. And we also can do faculae simulations. So one of the main differences with the faculae is that they actually form in the intergranular lanes. So a spot would suppress all of this structure, but the faculae sort of show up here as a bright feature between our granulation cells. So this is no magnetic field. This is essentially what we would assume the quiet star would be. And if we add some magnetic field, we see this formation of the faculae. Also shown here a different disk position. So this is right at the center of the star, and this is more towards the limb. So what you can see here is clearly this nice brightening by the faculae, and this comes back to what I was discussing here, that we're looking at the walls. So it's a simple geometric effect. If you look at the disk center, you sort of see into the tube. But if you now go to slightly different inclination angles, we're really looking at, disk positions, we're really looking at those walls here that are heated and that form those bright structures. Let me maybe take the statement of faculae being bright back, because, well, we know how they work for the sun. So this is a simulation now for cool star. And you see, depending on the magnetic field and wavelength, so for 100 Gauss, you still form nice bright features in the intergranular lanes. And then if you go to stronger magnetic fields, all of a sudden, those features become dark. And this is a rather complicated picture because a lot of things come into play here. It's not surprising that factly are dark around 1600 nanometers. That even happens on the sun. This is primarily caused by the opacity minimum by mostly this is caused by the atmosphere being dominated by hydrogen, and hydrogen has an opacity minimum at this wavelength. So we're essentially looking into a cooler layer of the atmosphere where hydrogen is more predominantly acting as the main source for opacity. So we're looking at something darker. And similar thing with the brightening here or other wavelengths. We're looking at deeper layers into the atmosphere. We have different opacities. And this is now more a cautionary tale that leads me to the discussion of how we want to solve the stellar activity conundrum. I think I made a point that, understanding the sun is good. And then based on, models that we have for the sun, let's see how they work for other stars. That has been the approach that I've been following. And I think it's a decently good approach. I'm not doing this alone. I mean, Ignacy just recently got awarded his ERC Advanced grant with Spotlight. And also we're working closely together with the ERC Synergy Grant Reveal, which was partially led by my PhD supervisor, Alexander Shapiro. So I think it's a very complementary approach here because on this side, we're having a lot of observers and machine learning specialists. And on this side, we have specialists. So Sarah Seeger essentially pioneered the idea of transmission spectroscopy. And Andrew Collet-Cameron is a well-known expert in spectroscopy and radial velocity. And Sasha essentially deals with all the radiative transfer pieces. So I think it's a quite good group. So what do I want to do? Well, I propose that we use models of stellar surfaces. In our case, we now will use the StarSim code that Nuno has been developing a lot further, plus this new 3D spectra that are based on first principles. So there's no assumptions that go in when it comes to mixing length theory or other things that was done previously. We use that to model the sun and the stars in different observables, directly compare those two observables, again, feed it into the model to do the inverse, and see how far we can actually now beat down the noise that's caused by the star. Specifically in transmission spectroscopy, that should help us find and characterize a planet like the Earth. And I think I will just leave you with my conclusions. I'm glad to take your questions.
Thanks a lot also for being nice for the time. So questions.
So thanks for the very interesting paper. When you showed on the spot for 3 different types of GS, yes. So the slow velocity that you find for the M dwarf, I think surface gravity means that it's not really low, right? So it's solar even higher gravity.
Yeah, sorry, yeah.
Surface, yeah. So could this be just related to the fact that the flux that needs to be put out is smaller per surface area? So a small velocity, since the convective flux is rho dq, maybe small v is enough to carry this.
Yeah, that could also be. I mean, it's always the question. So I mean, there's also magnetic fields imposed, right? So the magnetic fields even outside of that spot might have a little bit of an impact of the surrounding convective pattern. But if you're interested in that more, I mean, the paper was just out and they described all of this in great detail.
And okay, I have another question. So you showed the Macmillan sample and then the other 2 papers that increase the sample, but I'm not sure you showed how the new stars would fit into the variability
Yeah.
rotation period? How
Um,
would that change?
So it is also in my publication from 2023, but in basically, so the more or less like the McQuillan Santos sample, they overlap. Like Santos essentially found the same stars that McQuillan also found with similar rotation periods, so that's good, right? So what they found, there's even more stars down here, but the sun is still a little bit lower than those stars.
Yes. Yeah.
Thanks, Nina. And about the extreme case in which the inclination is zero, so we are looking at the body. There are two questions. So the first is, you mentioned that in endorse, or well, not in plastic data, there are basically very big spots in the pole. So the first question is, when you look at CDI, or you see that. The second is, for slow rotators like the sun, which you have two spots, whatever, and you look on the top. How do you get the periodicity? Because you lose the variability.
Yeah. So to answer your first question, yes, we know from Siemens Doppler imaging that if you go to those fast rotators, that we see more field spots towards the poles. And in our model, it comes naturally because what we are assuming are so-called thin flux rope simulations. So what we do is we have like have a seed field at the base of the convection zone, and you have a flux rope, and if it would come out at the surface, right, you have the two hook points that gives you your spots. And what we then do during the emergence of those flux tubes or flux ropes, we also have the Coriolis force, right? So if you're a fast rotating star, what happens is that this flux rope naturally gets deflected towards the pole. But this is how we form polar spots. It's one of the theories of how we can have polar spots on stars as well. The other theory is what you can also do is have very high meridional flow. So meridional flow is a poleward flow. So if you increase that, you also accumulate your flux fairly easily towards the poles. Your second question, yeah, it's correct. So I think I should have that in the backup. That's not really there. So the short of it, that if you look at the pole, you will not see any rotation. What you're seeing or what you're measuring is then really more related to the lifetime of regions. So there were a couple of other papers by Timo Reinhold and also of Veronika Witzke, where they looked more closely into also the impact of the inclination on your retrieved rotation periods. And interestingly enough for the sun, I think it was here. So for the sun, what we did is we simulated based on sunspot number. So we have simulations of the solar surface distribution back to 1600 essentially. So 22 solar cycles, something like this. And with our surface flux transport model, so we fed that in surface flux transport model, we got the full surface distribution, which means we could also look at the inclination more detail. And what it turns out that if you do that, the peak of the distribution when it comes to detectability of rotation periods is actually not at 90 degrees, but it's a slightly tilted value, namely roughly 60 degrees. And the reason why that is comes back also to the contrast of the faculae and the spots. So for the case of how we look at the sun, we're almost there where they're canceling each other out. This is why you don't see much of a peak here, a very broad peak. But if you just change the inclination angle slightly, you actually get out of this compensation regime. Another way to get out of this compensation regime is also would be to change the solar metallicity as well. But that's then related to more other stars than the sun.
But if you have zero, you should get exactly zero.
No, you still get some variability, but it's not variability that's caused by rotation.
Yeah, I'm speaking about the rotation variable.
No, yeah,
You
well,
will not get any peak.
not really, no.
Other question?
Okay, so you showed now in the previous slide that you showed to Daniele the 3D, so the full star map. Well, we also that one.
Yes,
For
yeah.
my purpose. Okay. So how are you building these full star models, right? So for the code you're using Muram, but that's just for. But
Just for the
box
spectra,
in
yeah.
That's the box in the star, right?
Yeah.
So then how do you?
So in our case, so Muram would come into place into here for the spectrum. This is completely independent of Muram.
Yeah.
So what we do, I mean, surface flux transport models have been around since the 80s. So we used one of those where you just assume that the flux is emerging as a bipolar region, and then you let it evolve under the influence of differential rotation, meridional circulation, surface diffusivity, and there's also some horizontal diffusivity, and you just let your flux do what it does on the surface.
Any other question? Also, any other? No. Go on.
So you talked about radiative transfer as well, and so that like appeared in this, but you're not doing any work related to synthetic spectrum here. Are you interested in that? So to do synthetic spectrum, right? So
Yeah.
if you do you do 3D line transfer for the synthetic spectrum on Muram, or do you maybe not do exactly but at MPS, right? Do people take the average and they make an average profile of the field and then do the transfer on top of them?
Yeah, no, I know what you mean. So those spectra here,
Yeah.
I've actually calculated them
Okay.
using the Muram cube. And as I said, there's different approaches, right? So you can either take like an average atmosphere of your cube and then run the radiative transfer on that. We take the long route and actually do calculations for each pixel. So for each of the roughly 500 by 500 pixels that we have, we run the radiative transfer because we also want to understand how convection affects the spectral lines, and then we can't really do just a cube average.
But when you do one pixel, you just take the vertical column.
Yes.
And you forget about the other parts.
We forget about the other parts of the pixel, yeah. So,
okay, so there's no scattering and things like that, right?
No. But also we don't do this just for one cube, we do it for at least 30 cubes so that we understand the time variability there as well. And also because Muram, I mean, it does have radiative transfer like in the gray approach. So what's a little bit missing is we don't have the back effect of radiative losses necessarily as a wavelength dependence because the radiative transfer is then separate of Muram.
Questions from the audience or online? Is there any question from? I don't know if there's anyone actually connected. Okay, so if not, let's thank our speaker again. I guess Pizza will wait for us, but you will